Okay.
All right, so I don't see your screen quite yet, Bruce.
Just 1 second here. I don't know why it just disappears like that.
No problem. Take your time.
It says pause. Why is that?
Not entirely sure. Maybe just try stopping and then starting again.
No, it doesn't like it doing that way. What did I do before?
So
Hold on a
let's,
second.
yeah, no problem.
Why does it keep bouncing up to the desktop?
Can you try sharing your full screen?
Yeah. Yeah, I want that one.
Which one?
That one. Stop it. Stop it. Let's go here. I'll move on. Oh,
Any luck there, Bruce? Oh,
yeah.
Perfect. That looks great.
Okay, we're ready. Sorry about that.
Yeah, no worries. Good to go.
Okay, so we're ready to go, right?
Yes, absolutely. Take it away.
Okay, so the this is just the outline of the talk, and so I'm going to cover the history and development of Lamontagne Geophysics Ltd, who was Yves, and what is UTEM, and then I'll go through some notable developments of where the company has gone and the development of UTEM over that time. We got to our latest development is what we call UTEM 5, or the fifth iteration of where we are, and it's just every edition has got bigger and better. I'll briefly touch on the basics of some interpretation and modeling of the EM data, outline the many successes that the system has had, and then just touch on the borehole inside the office here where I'm speaking, also the zero field Gauss chamber, some of the awards that Yves actually won, and some of the other contributions that Lamontagne Geophysics has made over the last 45 years or so, and the acknowledgements. So we'll just get straight to it. So firstly, it needs to be said that Yves passed away in January this year, and he was one of 10 children. And Yves actually privatized the system of UTEM, and has always been keen to develop geophysics and sell geophysics all the time in his working life. And so without further ado, we'll get on to what the story It stands for the University of Toronto Electro-Magnetics System, and it is a wideband time domain surface EM system that actually measures the step function of the ground. It was designed to achieve the sensitivity and interpretability necessary to handle problems of deep exploration, with the main objective being the search for massive sulfide mineralization. Yves privatized the system and coined it for himself in 1979. And with that, the system he had built, or he got approval to build, was called UTEM3, and he built 3 systems. Where we are today with the systems, it is developed much further in the 5th iteration, but now we have a very wide dynamic range. We can measure the 3-component EM data from up to 3 transmitter loops. That gives us 3 coupling angles, and we do this all simultaneously, and that just gives us superior target definition and improved definition of all targets. We have the capability to detect anomalies down to 0.01 picoteslas at 5 Hertz and above. All components of the system are linear with exact PE and DC. So the PE is pre-emphasis and deconvolution to measure the step response through all time. And what this does, it provides uniform sensitivity and allows us to discriminate between the different types of conductors. The picture on the left is actually a schematic detail of how the system works. So on the left there is the transmitter loop, and that transmitter loop has the primary field there. We have the surface noted and a subvertical conductor there, and then that presents its own secondary field. What we do, we understand exactly where our loop is, what the current is, and we subtract that loop from the data, and that's how we see what is left. So to do this, over the time of the development, going through the different transmitters, from UTEM1 through to UTEM5, we've always been trying to measure the square wave of the system response. And so UTEM1 and 2 was a triangular waveform, but from then on, it's always been attempting to have some PE-DC deconvolution to be able to accurately get this perfect step response. And just compare the thing. If we just look at how a moderate conductor looks and how our channels are displayed, this is the result we get for a moderate conductor. Okay, so and what's interesting is when we had UTEM3, we used to use the channel 1 to normalize our data, and then in the later systems we operate and have this little channel called channel 0, which is the latest time to normalize our data. If we look at a perfect conductor, what is very keen on this is it gives the perfect response. What is really interesting is that this is what the pulse systems cannot detect, and that's what I want to say there. If we look at the sensitivity of pulse systems compared to the UTEM system, ours is we're measuring that primary field, and then we reduce our data using channel 0. And what this is actually showing is that, or when we calculated all this, comparing the systems, in early times, we're saying that the system is 2 times better than a pulse system, and also 4 times better in late times. Some of the notable developments of how the system came about, Yves did his thesis project at U of T, and what was very important was from UTEM2, it was a University of Toronto and industry consortium that developed the ideas of where it was. Yves actually cannibalized UTEM1 to make UTEM2, but the commercialization of the system was in '79, and this is when UTEM3 came into being. And then the next development with UTEM3 was having, with Cominco funding, was that he first started on this accurate piece of actually calculating that step response. And then in 83 was the fiber optic link for the borehole for just the vertical component. 88, we had the induced source resistivity capacity of electrodes. And then by 1990, the system had been developed pretty accurately under the UTEM3 label for both the magnetic fields and the electric fields. It was in 1990 that Lamontagne moved to Kingston, and that changed things. From being in Kingston was the development of the 3-axis borehole probe and also the receiver, and that was all provided by INCO funding. And then the UTEM4 transmitter was developed, was a high power transmitter, and that was developed under Falconbridge and Kojima funding. Moving on, the development of UTEM was always there, and UTEM5 for surface was developed with the feedback coil, and we had the ability to change the stacking in the receiver. And then by 2014, we had the development of a medium powered transmitter. And then in 2016, well, to perfect the borehole systems, Yves felt at the time that he needed better procedures in place. So it was the purchase of the new building in Kingston around the corner from the first building, and the drilling of the borehole, the construction of the Gauss chamber. Everything was to get perfect data. And then in 2017 was the high power UTEM5 transmitter. And then from that time, 2019, during the pandemic, was the building of a production model of that UTEM5 transmitter. And this year, we're also heading through that transmitter through the certification program to make sure that we're on the right side of safety. So this is what the feedback coil looks like in the middle there. And in the left, you can see that it's very, very portable, and you can place it on the line to take the readings. The receiver can't be any closer than what you see there, because if you stand over the coil, that creates noise in the system. And on the right-hand top corner, we're looking at basically the sensitivity of the noise levels of that of the coil inside the Gauss chamber. Okay, so that's that. So basically, the Yves' idea was to be able to push it into a borehole system. So it's exactly the same sort of setup. So on the left, you see how the receiver attaches to, and the borehole probe is attached to a fiber optic cable, and it can go of the winch and the dummy wheel and the probes. Shows the mechanisms, all the design, everything about the system was all built in-house, designed in-house, built in-house, and then we do the surveys with our own personnel under our own safety guidelines, and we provide the services to the different clients. On the right is exactly what, from a borehole, what sort of response we would receive from an in-hole conductor. So we get a sharp peak off. It's got to be remembered that the system, or the longest cable, fiber optic cable that we have, goes down some 3.5 kilometers, and then we can see not only in-hole conductors, but we can also then predict off-hole conductors. In the middle there is a picture of the development of the latest production high-powered transmitter, and that transmitter is set up that it's totally hands-off. It's got a remote control there in yellow on the right-hand side. This is how the system is. So it's totally hands-off, and we can control the current and going through the loop, and work out exactly what that current is to be able to remove that primary field accurately. So this just shows an idealized section of a Sudbury borehole. And in this data, what we're really interested in is in this hole, we have both an in-hole response and an off-hole response. So the in-hole response is this peak here. That's the in-hole response. But then this whole piece here is the off-hole response. Okay, so what we have on these plots, that's all in 3C plotter, we have the primary field, and when all the fields kick, we know this is what we call this off-hole target is definitely basically a non-decaying target, is how we view it. So in the red, we have our vertical component, or called the axial field, and then our two horizontal fields are these two profiles. So to perfect the calibration of our coils, both the surface coils and our borehole coils, Yves reckoned that it was necessary to build a zero field Gauss room. And so when we moved offices, that's what we did. And so we cut a concrete pool and basically, and then built this inert wooden structure in the middle of it all. If we look inside the room, you can see how it's lined, and all that silver material is what we call perma-alloy, and this is to isolate or stop the it's to stop that field, that Earth's magnetic field, from entering the chamber. So by definition, a zero Gauss room has to have a minimum of 2 layers. And where we are with this is that we just have the 1 layer. And it's just incredibly expensive to buy this perma-alloy. So that's where we are. But what we do have, though, in the current setup, it's big enough that we can put the whole borehole probe totally connected, which is 6 meters in length, and we can rotate the whole thing a full 360 degrees. And the whole idea is to be able to do perfect calibration, orientation, to perfect the data that we can collect. So on the left there, you see the black coil, which is the surface coil, and on the left, behind the wheel, is the original zero Gauss chamber, and that's a 3-layered chamber, and that's where these coils were perfected initially. But now we can put the whole probe from the borehole and do exactly the same things. And it's all about getting perfect data, repeatability from every probe and every coil. So how does the successes work? I mean, UTEM itself, just in Sudbury, there's a number of very significant deposits that have been found in Sudbury. And before UTEM was actually used, there was like a 20-year gap where no new deposits were found. But as soon as we have the borehole probe, the success rate of being able to point and shoot in-hole and off-hole has found all these deposits. And that basically is the success of Sudbury to this day, that there's loads of reserves, everything's getting deeper and deeper, and there's more, we do most of the holes there, but what's going to happen is it's continuing to use the system. There is more mines out there to be found. It's been incredibly successful how the system has worked. And I'll come to give a couple of case studies from the surface, one of the borehole, that's to follow. So just how it works, showing you a decay curve against profile data. And then when we try to model these things, we tend to point and shoot using what we call a thin sheet approximation. And we're basically pointing to the middle of these thin sheets. And we tend to simplify things to make the system work. But when you point to the center of these plates, that's when we normally intersect the target. If we look at the geology in Sudbury, we have contact deposits and footwall deposits. And it turns out that these footwall deposits turn out to be even more rich than the contact deposits. But when we came to model these things, we model everything the same way in this first approximation. And we put plates on everything, and so the center of the plate becomes the target. If we look at VMS deposits, and what do? Well, we just do the same thing. Put a thin sheet over the whole lot. So, but there's certain deposits that this first approximation is totally wrong and very horrible. So what we actually do is that we can put in basically any parametric shape. And so Eastern Deeps, close to Voisey's Bay, we actually get a better approximation as the start-off model using a sphere than we do getting from the approximation of a thin plate. What we have the capacity to do now, we can basically place in any parametric shape, so we can have an ellipsoid or any shape whatsoever. We can actually cope with that and the response of that. So now we'll just look at a borehole situation of one of these mines. And so these holes are, as you can see, is from Nickel Rim South, 1,800 meters deep. You can see on the left the interpretation of the data of where the conductors are. Again, all these were intersected from the drilling, and this new resource was found. So this just shows you the boreholes in relation to how they quoted their ore reserves. So these are the lenses created from their ore reserves and their assay results. And in this deposit, there was a hanging wall resource and a footwall resource. And it's been a very, it's been very good. Talk about what happened on the surface and go to Australia. The change is for Q River was this changed the belief of the co-developers from Cominco. The company in Australia was called Aberfoyle, and it was the Aberfoyle people absolutely believed from this result that UTEM was the way forward. So we're in Tasmania, and the Q River case study really altered the thinking. The S-lens was actually an airborne target, but the S-lens was actually a barren sulfide unit, which everybody could detect, and it's clearly anomalous on this section here in UTEM. But the interesting thing was that this very subtle late time target in here corresponded with the PQ lens. And so this turned out to be very rich in massive sulfides, contain a lot of zinc. And you can see the conductance is only 20 Siemens, but it was clearly detectable. And for the Aberfoyle geophysicists of the day, this sold them on UTEM. They decided that if UTEM hadn't been completed over a project, they were willing to take ground and just do UTEM to work out, was there anything to chase in these prospects or not. So this deposit was 3 million tonnes, and they certainly made money out of mining that 3 million tonnes. So they also had the Halia prospect, and UTEM was then conducted over that prospect. And a large grid was put in place, and there didn't seem to be much in the data to the very last line, and then there was this subtle, very late time response, and this response was worthy to extend the grid, and the grid was extended, and then it was interpreted. And what this meant was the Halia was found, and the Halia was interesting because it went into, when they extended the grid went into or underneath a very conductive area. Conductive shales went over the top of it, and they felt they couldn't explore this area at all. But UTEM was completed over it, and as you can see, it's these very subtle late time things that were the targets. These crossovers, these changing crossovers, is because of that conductive shale over the top. But what was of interest was these very massive sulfides, and these things were like horizontal tubes of massive sulfide. But this was a phenomenal ore body. This was 6 times the size of Pure River and 17 million tons, and the zinc ran something like 20%, and it was because there's so much sphalerite that they said, how's this going to be found? But it was found by UTEM. If we look at Neves Corvo, the interesting about this one was this is in the pyrite belt in Portugal, and this is a huge VMS camp at Neves Corvo. And it was a test survey, and 2 loops were put out and 2 lines were read, and there's also a power line going over the mine plan. And where the test survey was actually conducted, it wasn't considered by Cominco of the day that this was terribly prospective, because there was no gravity anomaly associated with in the area. But anyway, UTEM was completed on those 2 test lines. And then out of it, over the power line, this part of the data was extracted from the data to see what was left. And again, it was late times, and basically the Lombador zone could clearly be detected before anything was drilled. So in looking, and this was modeled in multi-loop, and we had the A and B were like regional conductors, and then inside we had 2 ore bodies. So those 2 ore bodies was Neves North, and this grey zone here was known as Lombador. And the significance of this is that Lombador is, 800 meters down. It's UTEM 3 data. It was a phenomenal discovery. And it turns out that this is the biggest lens of any. It contains 200 million tons of sulfides. And so it was a very nice discovery. Now we'll talk about where we go with the Voisey's Bay and area, and we're going to look specifically at the Ovoid deposit. This is exactly what people want to try and find, and we're going to talk about how we could try and work out the results of the UTEM data and how we could model that. So when we look at the geology of the Ovoid deposit, the massive sulfides, or the bowl of sulfides, is in the bright sits beneath that. But circling this body, we have these troctolitic dikes, and they are regionally conductive, but not conductive like the Ovoid deposit. The massive sulfides act as a superconductor, and they behave like with a conductance of something like 20,000 Siemens. And it's how we could try and model that. This is just a picture of the ore. It's just pure metal. And so the bulk of it is pyrrhotite, but there's still such a high amount of pentlandite and chalcopyrite in the ore body. And it's just a classic bowl of metal that was clearly mineable. And that the ore mined there is valued at 15 billion. So Yves said, well, I think we can do this finite difference method of forward modeling called MGM. And so MGM stands for multi-grid EM. And this is a multi-grid. And that section of the mesh underneath there in black there shows the dimensions of the mesh. And we can get finer and finer, and then you can calculate the responses in full 3D. And it's a forward modeling process that we get finer and finer. When we get to the finest mesh, in this case, we went down to a mesh size of something like 2 meters. So if we could fit the data, we have a very accurate result. It's not an inversion. It's a forward modeling process where you have to drive that model. And in this case, it was driven something like 100 times to be able to explain the geology. And that's what we'll go through. So on the left, you see the response. And these are some of the most spectacular anomalies seen. So the red is the vertical component, and the horizontal component is in blue. And on the right is the geology and how that was mapped out. So we're looking in the top section there at a depth of 36 meters. This is the looking top down onto the bowl of metal. And then the bottom picture shows the cross section. And you need to just hold in your head the schematic picture of in blue of how this has to connect to make the forward modeling work. So the breakdown of this process was, so the top picture here of the vertical component and the cross component is in A, all the field data. So that's what we're trying to connect to. And these are phenomenal anomalies. They get, staggering. So the top one is what we're trying to get to. Then the next section B shows the modeling of the ovoid just with the overburden in the half space. And we're getting roughly the format we want, but we're not there yet. And then the modeling concentrated on adding in the troctolitic dikes. And now we're starting to get the response, but we don't get the amplitudes. And when we put if we look at the bottom picture and you put the troctolite in with a conductive channel connecting everything together, now we actually get a pretty good fit of the data. So it's a tremendous result. If we had a borehole into the same thing on the left, we see the predicted response of the vertical plus the two cross components. It's a staggering anomaly. And when we see everything kick off in the vertical field or the axial field, we can see how everything kicks up. And so this is just acts like a perfect conductor. We can go in the right-hand picture, we can go well off to the south, and we can still see the whole thing as a classic off-hole target that cannot be missed. And so that's the story of the modelling from the ovoid at Boise's Bay. So this is just a picture of putting the borehole in the office, and this is Yves at work late at night. The hole was drilled down to something like 630 meters depth in the office, and Yves was concentrating on wanting to make sure this hole remained open. So this is where he's trying to put down the hole, all these cuttings to line the hole or seal the hole so it doesn't collapse. But it went through the limestone in the office and into the basement rocks underneath, and there's just different shear zones and stuff in the hole, and but it's all been lined with to be kept open, and that was the process. So Yves never stopped. That's all I want to say. A couple of the awards that Yves won was was in 1984 as the one on the left from the SEG, and exactly the system that we've been talking about, measuring the step response of the ground. This won the Best Paper Award in 1984. And then in 2016, Yves was awarded the Cecil Green Award from the SCG. And he's a very worthy winner of that award. The Cecil Green Award recognised an individual who has demonstrated courage, ingenuity and achievement while risking his or own resources in developing a product, service, organisation or activity that made a major contribution to the geophysical industry. So he was a brilliant technical innovator and he had a major impact on the mining exploration community in developing and advancing the UTEM time domain EM system. In conjunction with that, he's developed all the modelling software and basically the business has been running for the last 45 years or so, and there's been many UTEM surveys done worldwide. So there's been many other contributions, and those contributions consist of things like nobody else even dreamt of putting a fibre optic cable down 3.5 kilometres in Sudbury. So he was the first to have done all that and got everything all working. He's had a terrible amount of success. He's been a big contributor, or Lamontagne has been a big contributor to the PDAC, and as part of the PDAC each year, it was routinely visited. What was routinely visited by everybody at the PDAC was the Lamontagne parties, and these were terrific events. They got harder and harder to put on, but it was the go-to party of the PDAC during Yves' time. And so just want to point out that Yves did many, many great things. It was always considered that everybody knew that whatever was developed, he always put the money back in, and he continued to develop everything. And basically he lived, dreamt, that's all he wanted to do was perfect the system. And he never left any stone unturned in trying to develop the best system he could. And basically that's where I'd like to leave it.
Thank you, Bruce. Very much appreciated this presentation, and great to see, the evolution of UTEM and the impacts it's really had in the field and the impacts Yves has had. So would like to open it up for questions from folks. Would it really encourage people, if you have a question, to raise your hand and we can unmute you and you can jump in. It's a lot more engaging to have a bit of discussion rather than me being the one to ask all of the questions, but I'm happy to do that if you like. I see there's a couple questions in the Q&A, so I'll pause and see if anybody from there. So Tyler, Yagua, Longying, if any of you would like to raise your hand and jump in, I would welcome that. So I'll give you a moment to perhaps do that. But if not, I'll ask those questions. All right, so I see Yagua has, so let me allow you to jump on in. Thanks, Yagua. You can unmute and ask your question.
Great, thanks. Yeah, Bruce, thank you so much for a very informative presentation. I have two questions quickly. One is more general, another is technical. But general question is, how do you think we can use the legacy of Yves Lamontagne to inspire more young geophysicists into the EM and into the resource exploration?
I think just by spreading his story is the way forward. And there's a couple of people. The guy that nominated Yves for the award he won in 2016 was Alan King. He's working in a committee with Gordon West, and there's a whole team of people working on how there should be some sort of legacy for Yves Lamontagne. There's also talk of him being admitted to the Canadian Mining Hall of Fame, and I think he just needs the support, because the acknowledgement should now come. I don't think he received the support while he was alive, but I do believe it should be, he should receive the support now. I don't think anybody comes close to him.
Thank you. And the technical question I have is, because I know that UTEM survey has been used in Raglan for mapping the ultramafics in the nickel deposit. And so I'm curious, what's the largest ultramafic unit you've managed to map with the UTEM?
Largest. We've mapped
deepest,
many.
yeah, deepest ultramafic unit.
For Mine Raglan, we've been involved in plenty of. We're not involved in everything they do there, but we've been involved in plenty of project generation work there over their areas. So when I say the internet says we've had great success in being able to predict and say where to go. In Yves' legacy of where does he appear, the other people that did a lot of work there was they've done a lot of geophysics in Mine Raglan, and they've done a lot of pulse systems and other systems, plus they've done squids, and these things have led to success. So the likes of Kathy Foley, which she's the head scientist now in Australia, her legacy from being up there is, they credit her with something like a value of $8 billion is the legacy from the high temperature squids used there. I'd hate to think what the value of Yves' legacy in finding deposits, but I think you can multiply it by 10, and now you put Yves where he should be.
Thank you, Bruce.
Does that answer your questions, or you've got anything else to add?
Yeah, no, that's fine. Yeah.
Thanks, Yagua. I see there's a question here from Tyler Matheson. The system would have been based in analog electronics, and in particular, operation amplifiers to integrate the secondary signal and perform other operations. By saying that the system is measured through full time, does this indicate that the system is largely still analog? Or, and he mentions here the analog electronics are very good at removing noise with common mode rejection. Is that particularly why the system performs really well? So I guess asking basically, are analog components still a big part of UTEM or not?
No, it's a digital system. Not quite where it's all built in that in real time we can see our data and see everything. We can interpret it pretty much in pretty close to real time. I'm not sure where he's going from analog to digital. That's not where we are.
Okay, thanks. All right, I see Chris Nind has a question, so I'll allow Chris to jump in. Chris, you're welcome to unmute if you like.
Am I unmuted? Can you hear me?
Yes, we can hear you.
All right. I just wanted to thank Bruce for an excellent presentation. And just a couple of things that's always very much impressed me by UTEM. I had the honor of using UTEM in the field in 1980 on a fairly large survey in northern Saskatchewan. I've always been very impressed by a couple of things, not only Yves' dedication, but to the technology, but also Yves' understanding of field crews, and and his equipment was always fairly portable. It was comfortable to use, and unlike some other systems that I've had the chance of using in the field, Yves, the UTEM system was a pleasure to use. So that is something that I think all equipment designers should keep in mind, and Yves always kept that in mind. The other thing that always impressed me was that as the range of conductors that the UTEM system was able to detect. some of those ore bodies that you were showing in New Zealand, I take it they were full of zinc, and that's not particularly conductive. And yet it's very good at the perfect conductors that you see up the nickel up in Raglan and things. The range of conduct of the UTEM system was truly extraordinary, I thought. But thank you.
Just before you go, I think one of the biggest things you've said there is about how he knew the end product before he built it. So for the likes of UTEM3, the box of the receiver is actually built first, and then everything else was made to fit inside it. That's how he thought. So he's just incredible.
Yeah, agreed. Thanks.
Thanks, Chris. I see another question in the Q&A. So Longying is asking about if it's possible to do urban TEM borehole surveys, or perhaps any other just different, you could speak to any other settings or scenarios that are perhaps a bit unusual where maybe UTEM has been used.
I'm not quite sure where that's going, but I'll attempt to. The borehole is like a hybrid. As it's got better and better, so the borehole probe, or UTEM5 probe, when that was actually constructed, that it was impossible to downsize it to fit into an NQ hole. And so that's where that sort of stopped. But for the minute, because nobody is drilling NQ holes except for the odd one, and usually shallower holes and shaft holes and things like that. So that was not going to be a winner as it stands. But in that, what he basically the compatible have exactly the same design, where we can interchange our personnel, we can interchange our receivers and transmitters, and we're using exactly the same equipment in both surface and borehole systems. So everything's, and that's how we get this, what we call UTEM4+. It's an integration of how we can latch on to UTEM5 equipment, but we can also latch on to extending the value of the current UTEM4 probe. So we've had some developments, and we know that the UTEM4 probe is certainly better than when it was first developed, and in how we're constructing them. So one of the biggest things to be noted is that Yves has researched all these things. He always left no stone unturned of exactly what he wanted to do and to find the best alternative. So that ability is what puts him apart from everybody else.
Yes. All right. Thank you, Bruce. Really appreciate your talk. I see some thanks coming into the chat and into the Q&A. So very much appreciated. Thanks for your presentation. And we'll have this posted online soon for folks to be able to watch and follow up on.
Okay. Thank you.
All right. Thanks.